Part 9, linearizing data. We saw in the last section that we can take data, graph it, and with a linear function, draw a best fit line through the points and find the slope of those points to get physical meaning from our data. But what if your data is not linear? What if it's quadratic? What if it's a square root function? What if it's an inverse function? There is a way to linearize, that means turn nonlinear data into a straight line. I'm going to show you how to do that. The directions tell us that we need to plot each set of data and identify the relationship between the variables. Write a proportionality between the two variables. That means come up with an equation. Then replot the data so that you get a straight line. Use the empty rows in the table to calculate new values. Draw a best fit line, find the slope, and then write an equation for the line. Okay, there you go. So the first thing we're going to do for number 37 is we're going to graph acceleration on the y-axis, and we're going to graph mass on the x-axis, okay? Now, you'll notice that your acceleration, your largest acceleration is 4. Notice your acceleration is going down as your mass is going up. You ought to have a clue right now as to what kind of graph that is, right? That's definitely not an increasing model. But your largest acceleration is 4, so how can we do that? Well, we can go something to the effect of maybe 1, 2, 3, 4. Every couple boxes, 4. That seems to work. And then our mass, our highest mass is 30. Well, let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Well, we have 20 boxes going across for essentially getting 30. So probably need to go by 2, I'm guessing. So 2, 4, 6, 8, that would be 10, 12, 14, 16, 18, that would be 20, 22, 24, 26, 28, that would be 30. So that scale would accommodate both sets of data. All right, now you plot. So at a mass of 5, we have an acceleration of 4. That's exactly right here. At a mass of 10, you have an acceleration of 2. That's exactly right here. At a mass of 15, you have an acceleration of 1.4. Well, where's 1.4? Well, 1.5 would be exactly right here. 1.4 would just be a little less than that. Okay, at a mass of 20, we have an acceleration of 1. You can already see the model is decreasing. The acceleration is decreasing as the mass increases. At a mass of 25, we have an acceleration of 0.8. That'd be a little less than 1. And then finally, we have, at a mass of 30, you have an acceleration of 0.67, which is 2/3 of the way. So not quite 3/4, right, but more than a half. So there's our model. There's our function. Okay, draw a curve through that. And that is, of course, an inverse function. This is your typical 1 over x function, okay? Now, based on this model, what do we know? We know that acceleration would be equal to essentially some constant value over the mass. Okay, so we're kind of dealing with that, all right? Well, how can we get this thing linearized? Well, this is supposed to be on the y-axis. Clearly, mass is on the x-axis, but if we plot mass as is, we get this decreasing function. But what if we try something different? I'm going to rewrite this. And the equation, of course, we're using is Newton's second law, right? Net force equals mass times acceleration. We just solved for acceleration. So what I'm going to do is I'm going to split this up into A equals 1 over m times, F times 1 over m, right? Because multiplying by the inverse of m is the same thing as dividing by m, okay? Well, now it'll fit because we can match it up with our slope-intercept equation, y equals mx plus b. You guys can see acceleration is still on the y. So I'll plot acceleration on the y still. We can also see that our mass, it's not the mass on the x-axis anymore, it's 1 over the mass. It's the inverse of the mass. That's what we're gonna have to do over here. So we're gonna take 1 over the mass, which would have a unit of kilograms to the -1, or 1 over kilograms. Okay, so we need to inverse our second row. Okay, so let's take a second to do that. If we go 5 inverse, we get 0.2. If we go 10 inverse, we get 0.1. If we get, 15 inverse, you can see it's getting smaller, right? 0.067. 20 inverse is 0.05. 25 inverse is, oops, let me erase this, 0.04, and 30 inverse is 0.03. Well, clearly you can see the largest inverse of your mass is 0.2. So we can kind of scale it like this: 0.02, 0.04, 0.06, 0.08, 0.1. 0.12, 0.14, 0.16, 0.18, 0.2. So we can scale it much like that. As far as your y-axes, I would say just go ahead and scale it pretty much the same way. 1, 2, 3, 4, 5, because you have a similar number of boxes going up the y-axis. Okay, now we replot. So and I'm kind of start from this end first. Keep in mind what I'm plotting here. I'm plotting this on the x-axis and this on the y-axis. So this row goes on the x, this row goes on the y. So 0.03 and then 0.67. Now where's 0.03? Well, this is 0.02, this is 0.04, so 0.03 is right in the middle. So we're gonna go 0.03 and then up 2/3 of the way, right? Remember, 2/3 is little, it's kind of between 1/2 of the way and 3/4 of the way. Okay, so there's my first point. Now I'm gonna plot 0.04 and 0.8. So 0.04 is here, 0.8 is in between 3/4 of the way and all the way to 1. Now I'm gonna plot 0.5 and 1. So 0.5 is here. Sorry, I misspoke, 0.05. 0.05 is here, go all the way up to 1, and you can see your data is lining up in an increasing linear fashion, just like we want it to. Then we're gonna go 0.067 and up 1.4. So at 0.067, where's that? Well, here's 0.06, here's 0.08, here's 0.07. 0.067, right, is about right there. We're going up to about 1.4. This would be 1.5, so you're obviously a little less than that. Okay, then we're going up, let's see, over to 0.1 up to.
Javier Orozco, please report to the main office. Javier Orozco, please report to the main office.
Then we're gonna go over 0.2 and up 4. And you see we get almost near perfectly linear graph. Not just linear, this is a proportional data because it goes right to the origin. It's perfect. Okay, so now we need to find its slope. So go ahead and find 2 nice convenient points. I like this point here, and this point is pretty close, but it's not exact. I like this point up here too. So I'm gonna make a slope triangle, go up, go over. My rise is what? 1, 2, 3.5. So 3.5 is my rise, and my run, 0.02, so 1, 2, 3, 4, 5, that's 0.1, 0.12, 0.14, 0.16, 0.18. 0.18 is my run. All right, so my slope is going to be 3.5 over 0.18. And we get 19.4. Okay, now what are the units? We have meters per second squared over 1 over kilograms. Okay, well, if you divide by 1 over kilograms, you're really multiplying by kilograms. So what you get is you get kilograms times meters per second squared. Well, what is that? That is a Newton, right? That's the unit of force. So we're talking about 19.4 newtons of force. Okay, now we need to come up with the whole equation. All right, so A would equal 19.4, that's the slope, times 1 over, you can say times 1 over mass, you could do it that way, or we can go 19.4 divided by mass. Either way is fine. And notice there's no y-intercept because you're going right through 0. All right, in our final question, we're going to plot displacement versus time. We're going to plot displacement on the y-axis and time on the x-axis. Both are starting at 0, 0. That's convenient. My y-axis data goes up to 25. So let's figure this out. I can go 2, 4, 6, 8, 10, 20, let's see, 12, 14, 16, 18, 20. 22, 24, and I can estimate, this would be 26, I can estimate 25 right off the top. So I can kind of make it work. The x-axis data is going to be simple because I can literally go 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 10 to get to your full 10 seconds. So this data is going to be very easy to plot. So we have a point at 0, 0. We have a point at 2 seconds up 1. That would be exactly right here. We have a point at 4, 4, that would be right here. We have a point at 6 seconds up 9 meters, that would be here. We have a point at 8 seconds up 16, that would be right here. And then our final point is at 10 seconds, we're at 25, which is way up here. So you can see we get a quadratic model. That's your squared model. Okay, y equals x squared. Okay, but it's not linear, so we need to linearize it. So we're going to start with this. So basically, x, which is this variable, equals, since you're starting with no, since we're starting with no initial speed, and we can see that because the slope of a position time graph is velocity. And since I'm starting with 0 slope to begin with, I'm starting with no speed. So the equation we can model this with is 1/2 times a times t squared. Okay, where if we match this up to our slope-intercept equation, y equals mx plus b, we get
students, the cafeteria is open for
we get
breakfast.
x on the y-axis.
For all students, cafeteria is open for breakfast if you'd like to stop by before the bell rings. Again, cafeteria is open for all students to get breakfast.
Instead of t on the x-axis, we'll plot t squared. Which would be seconds squared. So this would be 0, 4, 16, 36, 64, and 100. Okay, my displacement is going to have the exact same scale. So 10, 20, okay? But my time now needs to go up to 100. So instead of each box being 1, each box is now going to be 10. So 10, 20, 30, 40. This will be 50, 60, 70, 80, 90, 100. So we got to rescale it a little bit. So this is going to be time squared in seconds squared. This is still x in meters. This is going to be a position versus time squared graph as opposed to position versus time. Okay. So the plot, 0, 0. Okay, we're going to go over 4 and up 1. Now, over 4. Well, here's 10 right here. So over 4, up 1 puts us kind of right there. Okay, then we're going to go over 16, up 4. So let me replot that. So there we go, over 16. So that'd be part way up 4. So over 16, up 4, kind of like right there. Then we're going to go over 36, up 9. Okay, where's 36? Well, this is 30, this is 40, 35, 36, up 9 would put it right there. You can see how the graph is taking a linear shape now. Okay, so we have 1, 2, 3, 4. Okay, 64, go over 64. So this is 60, this is 70, go a little less than halfway, and then up to 16. Should be right there. Okay, and then finally, over 100, up 25. Okay, and we get a nice linear model yet again. Okay, I like this point right here, and I like this point right here. So go ahead and find a couple convenient points to find your slope. My rise appears to be 10. My run appears to be 10, 20, 30, 40. Okay, so this time my slope, I'll write it over here. This time my slope is going to be, so 10 over 40 instead of 10 over 4, so 10 over 40, which is 0.25, right? 1/4. 0.25 what? Meters over seconds squared. Okay, meters over seconds squared. Okay, so putting this together, here's our equation. X equals, okay, now we're gonna, in place of our slope, okay, in place of our slope, we're gonna go 0.25 times t squared. All right, and there's the equation that models this.